Welcome back to Part B of our chapter on inventory management. In Part B, we're going to be looking into one of our inventory models, and that will be the economic order quantity inventory model. So one of the questions that any replenishment planning system needs to answer is how much should we order, or how much should we make? So we're going to be looking at several inventory management models that will help us to answer this question. The first one we'll refer to as the basic economic order quantity model. The assumption that we make on this one is that there are no discounts. And the other two we'll be looking at in other sections of this particular chapter. So in Part B, we're going to be looking at the basic economic order quantity model. And what we're going to be seeing is that under certain conditions, it is possible to come up with an optimum quantity to order. An optimum quantity to order that will minimize the sum of our annual costs for that item. So the basic economic order quantity model is attempting to identify some quantity to order that will minimize our total annual inventory cost. And the two principal costs that we are minimizing is the inventory carrying cost and the inventory ordering cost. Now, there are some very important assumptions that this model is based upon that are shown on this slide. And quite a few of these assumptions is very difficult, at least from my work experience, to find actual instances where these assumptions are true. So one of the assumptions is that the annual demand for this particular item is known, that we know what that is. Well, that's hard to do. You know, we've talked about how forecasts are very uncertain at best. We've said that forecasts are always wrong. So knowing the annual demand is a very difficult task. Another assumption is that the demand for this particular item is even throughout the year. In other words, it's constant. We have a constant demand every day, every week, every month. And again, having a demand that is even, that's a difficult thing to really identify that. Also, we assume that the lead times, there's no variability there. We assume that the supplier who we order this from, that they deliver the entire shipment in one delivery. And then finally, as we said before, we assume that there are no discounts in price if we buy in larger quantities. So let's take a look at the model for these assumptions. So this is the economic order quantity model. So our horizontal axis here is time, and our vertical axis represents our inventory level, some quantity on hand of inventory level. So if we start at the intersection of both axes, we assume that we receive a shipment in from a supplier. So we have a certain quantity on hand. And as we start to move forward in time, we start to consume or reduce our inventory by some constant rate. You can see that that is a straight line. So if it's a straight line, we assume that it has a constant slope. So we start to reduce our inventory. And then finally, we reach a certain inventory level that we refer to as the reorder point. So if you look at the vertical axis, you'll see the two words reorder point. So when inventory reaches this point, we're going to place a new order for a resupply. So we place an order with our supplier, and we're assuming that our supplier is going to deliver in their standard lead time. And just as we run out of inventory, so we're continuing to use inventory while the order is being processed by the supplier. Just as we run out of inventory and reach zero, the new supply comes in and we go back up to a quantity and we continue down through another cycle. So this cycle of reducing inventory by some constant rate, at some point reordering, getting a shipment in, and repeating that cycle, we assume that this is going to recur over and over again over a year time period. So this slide is essentially the same information. The only thing that's different is I have written in the text average inventory. So one of the cycles from the time that we start out until the time that we go down to zero, what is the average amount of inventory that we have during this particular cycle? Well, our accounting friends have come up with a very simple and effective way of answering that question, the average amount of inventory. And the way that they do it is something like this. What is the inventory at the beginning of the cycle? So if you look at the graph there at the very beginning, it says receive the order. So the inventory at the beginning of the cycle is some quantity we'll just represent by the letter Q. What is the inventory at the end of the cycle? Well, at the end of the cycle, we don't have any inventory. So that is zero. And then we're going to average these two numbers together. So Q plus 0 divided by 2 is essentially the order quantity divided by 2. That is the average inventory of a cycle. And since the cycle repeats itself over an entire year, the average inventory that we would have over an entire year would be the quantity that we order divided by 2. Now, the annual cost associated with this inventory item, the two principal costs that we are concerned with is the annual holding cost and the annual ordering cost. Now remember that holding or carrying cost is that cost associated with keeping an item in inventory for usually a year. How long, what does it cost us to keep it in inventory? And the ordering cost is the ordering cost every time that we place an order. So the letter H represents the holding cost. S represents the ordering cost. We have another variable, the letter D, which represents demand, and almost always the demand is associated with annual demand. So if this is total annual cost, everything in this formula needs to be annualized. You may have a homework problem that might state that we use 1,000 units, or we have a demand of 1,000 units per month. In calculating the total cost, that demand will need to be converted to annual demand. So if we have a monthly demand of 1,000, the annual demand would be 12 times that, or 12,000. So the annual holding cost is the average inventory, Q over 2, which we saw in the previous slide, multiplied by the holding or carrying cost per unit. The annual ordering cost is the demand divided by the quantity that we order. When we divide the demand by the quantity that we order, what we are essentially doing is converting that into how many orders we're going to place each year. So let's say that I have an annual demand of 1,000 and my economic order quantity is 1,000. So how many times will I order a year if I always order 100 with a total demand of 1,000? So 1,000 divided by 100, I'm going to order 10 times a year. And then I'm going to multiply that times the ordering cost per order. So every time that I order, what is that cost per order? So this slide shows the two cost information. The holding cost, you can see that the holding cost is a linear function, a straight line. The larger our quantity that we order, the greater our average inventory will be, and therefore greater our holding costs will be. The ordering cost is actually a descending cost order. So this ordering cost, I'm essentially amortizing it by the total cost, and it goes down. And the red line is the sum of each of those two lines, and that represents the total cost. So at any point on the horizontal axis, I can pick up the ordering cost, add to that the holding cost for that particular point on the horizontal axis, and that will determine what the total cost will be. We can see that the total cost is a U-shaped curve, and there is a minimization point. There is a point where the total cost reaches a lowest level. So that point where the total cost reaches its lowest level, if we were to extrapolate, so you see the red line going down to the horizontal axis, that would represent what the optimum order quantity will be, the quantity that will give us the least total cost. Now I ask you to call your attention, now this is important, call your attention to the fact that the total cost occurs at the intersection point of the holding cost and the ordering cost. So what that means is at the true economic order quantity, these two cost parameters are equal to each other or should be very close, within pennies of being equal to each other. So, solving the equation for the optimum quantity. We could use calculus, which would be the difficult way to do it. Another simple way to do it would be to take the carrying cost, which is Q over 2 times H, set it equal to the ordering cost, which is the demand divided by the quantity times the ordering cost, or D over Q times S, set those equal to each other, and just solve algebraically for the variable Q. And either way, we're going to end up with the formula that the optimum quantity is equal to the square root of 2 times demand times the ordering cost, S is the ordering cost, and then divide by the holding cost. So let's take a look at our case study. So in our case study, we know from our ABC analysis that our item crust represents the highest cost of all of our items. So let's calculate the economic order quantity as well as how many orders we would place each year, as well as the cycle time, that is, how much time is going to elapse between two consecutive orders, and then also what is the minimum total annual cost. So we need some information to be able to calculate all of these parameters. First is the holding cost is represented as $1.20 per pound per year of crust. So what that means is if I kept 1 pound of crust in inventory for 1 year, it would cost ZZ's $1.20. The ordering cost is $4 per order, and the store is open 364 days a year. So with that information, let's first calculate what the economic order quantity should be. So I've written in this slide the values of the parameters that we need. So our annual demand is 1,000 pounds. The holding cost is $1.20. Ordering cost is $4. So we can calculate what the economic order quantity is. So you can see that I've substituted the values for the variables, and the calculation is 81.6 pounds. But I really can't order 0.6 of a pound from my supplier, so I'm going to have to round that up, and I will use order 82 pounds. The next thing that we want to do is to calculate how many orders we would place in a given year. So the formula for how many orders that we would place in a given year is the annual demand divided by the economic order quantity. So the annual demand is 1,000. Now, in this case, students, what I have done is I have used in my economic order quantity my unrounded value that I had from the previous calculation. And the reason why I'm doing it as opposed to using 82 is if I take the rounded value, it's going to make this number a little bit less precise. So I get a little bit more precise answer if I use the unrounded number. Now, for homework or for exam purposes, that is not going to make that much difference, so don't worry about rounding or unrounding. I know a lot of students seem to get very anxious over things like that. It's just not worth getting anxious over. So the orders per year is about 12.3 orders per year. Well, you can't really have 3/10 of an order. It has to be an integer value. Orders per year, how many times do I place an order with my supplier? So this has to be rounded to 13. So 13, that sounds like that's, how many months in a year are there? There's 12 months in a year, okay? Well, 13 times in a year, okay? So I bet you that the next question on the amount of time between the orders, the cycle time is going to be pretty close to a month. So let's go through the calculations here. So what is the cycle time, the time between the orders? The formula for it is our economic order quantity divided by the annual demand. It's actually the inverse of what the orders per year is. It's the opposite. It's the economic order quantity divided by the annual demand, and then multiply that times the number of days that are worked per year. So if I go through the calculations here, what I end up with is about 29.7 days, or, I can't have 7/10 of a day. We'll round that up to 30 days between the orders. So that sounds about right. Okay, we got 30 days, about 12, 13 times a year. It's going to be about 30 days that occur between each order. Now, on the formula, when you multiply the number of work days, there is a possibility that you might have a problem where it states that you work so many weeks per year. So if that information is given, then multiply it times the work weeks per year. Don't try to convert work weeks into work days because you're usually not going to be given the information, does the company work 5 days a week or 6 days a week or 7 days a week? If you start to try to assume information like that, you're just going to get yourself in trouble. So if you're given information on the work weeks per year, just multiply it by the work weeks, and the time between the orders will be represented in weeks as opposed to days in this example. Now, the last thing we need to do is to calculate what the total cost of ordering and carrying the inventory would be for this item crust. So the formula for it is shown at the top. So the Q over 2 times H is that portion of the total cost that's related to the inventory carrying cost. The D over Q times S is that portion of the total cost that's related to the total ordering cost. So substituting our economic order quantity, you'll notice that I again use the unrounded number, 81.6. And doing the calculations, you can see that the portion that is related to the holding cost and the portion related to the ordering cost are essentially the same number. They're just within pennies of each other. So at the economic order quantity, these two numbers should be either equal or very, very close within pennies of each other. So the answer is that the total cost for this item for ordering and keeping an inventory is $97.97. And this concludes this part B of this chapter.